that around the black hole there's the probability of photon pairs evaporating from vacuum, and one of the photon would be trapped by the black hole, and the other photon would escape and radiate away, which we now call it the Hawking radiation. But since it's very hard for us to analyze or to capture these physics events from the black hole, we still don't have evidence of direct measurement of Hawking radiation. Now we have proposed an experiment that we can do in the lab to mimic the Hawking radiation effect, which is the analog black hole evaporation via lasers experiment, which is also called the Annabelle experiment. In this presentation, we will focus on the motivation and experiment setup of the Annabelle experiment, and also the development of the Hawking detector, which we propose to use the superconducting nanowire single photon detector, the SNSPD, to work with. So first, from the equivalence principle, you can see that on the left-hand side is the ordinary Hawking radiation, where we have the event horizon here, and the partner modes are trapped with the event horizon, and the Hawking photons would escape and radiate. Equivalently, if we have a accelerating mirror moving near the speed of light, and it has a very large acceleration a, which with the equivalence principle, it's like the large gravitational field around the black hole. So creating a high acceleration would cause a similar effect, which we have the event horizon of the mirror here, and capturing the partner mode and evaporating the Hawking radiation. And this is how we would like to do the Annabelle experiment with. So with a very intense laser, and the physics would happen inside this gas, which is been shot out by the gas nozzle. So the high intensity laser would create a wake field, plasma wake field inside these gas. And since we put a blade, we would put a blade right here, causing a high density gradient. This would cause a high acceleration plasma wake field mirror moving along with the laser. So there will be the Hawking photons radiating back, and the goal of this Hawking detector is to detect these Hawking photons. But also, because the event horizon of this experiment, which is the plasma mirror itself, would end when the laser comes out of the gases. So eventually, the event horizon would disappear, letting the partner photons also penetrating, and which is what we will do here with the EUV partner photon detector to detect the partner photons. So in particular for the Hawking detector, it requires a high, almost 100% single photon detection efficiency, because these events are very rare, even if we have very high intensity lasers. And also we need the IR broadband sensitivity, which expands from 2 micron to 100 micrometers wavelengths, because the Hawking photons radiated from the plasma wave field mirror is estimated between this region, and we need a low timing jitter and fast recovery, and also the polarization sensitivity to first get rid of the background that would be also radiated from the plasma wave field, which are not the Hawking photons. And also we want to do coincidence with the EUV partner photons, because the Hawking photons and the partner photons would be entangled, so the polarization and the timing would be correlated. So we would like to use the SNSPD detector. It is a superconducting detector, and the working mechanism is shown on this plot. The bias, we would have a nanometer wide and thin wires, and we would add bias currents to it, and when a single photon hits it, it will cause a hotspot, and the hotspot would expand, and eventually it will break the enough Cooper pairs to create an ohmic state, and this is where we will get the signal from, and then the hotspot would be the heat of the hotspot would be transferred to the substrate, and eventually it will come back to the initial state. So this is the whole cycle of one single event, and the SNSPD has very good recovery time. So here is the proposed characterization for the SNSPD with a single photon source setup. We have the lasers with ND filters to filter it to single photon level, and will be focused onto the SNSPD sample within the cryogenic system we have right here. And then the signal will be read out with the RF readout chain, including the amplifiers amplifying to a reasonable signal output, and we would read it out and get the single photon event of this. So this experiment is very exciting, and hopefully this R&D of the SNSPD will not only shed light for the Annabelle experiment, but also to other quantum information or quantum computational experiment. Thank you.